Hi. As you all know, I've been working on a small robot for the Wurth-Midcom design challenge. Unfortunately, some things happened along the way and I didn't really account for any slack in my planning, so I haven't got anything in the real world yet. Tomorrow I'll start doing the routing on the circuit board and I'll see if I can set up a Twitch account so that some of you can follow that live and maybe even ask some questions if you want to. Of course, if I manage, those videos will also be on YouTube later. However, I'd like if you still vote for me, just to show your support or to show me that you liked what I've done so far and hope that I keep doing it, or maybe just to get me that 3D printer so that some of the mechanics later on will be easier. But if you don't vote for me, which I'll fully understand, then please go to the Wurth website and vote for someone else. I don't mind losing, but it's important that as many people vote as possible, so that Wurth and other companies see that you really appreciate these kinds of things and that more people will start organizing these kinds of contests so that as many people as possible can have the kind of fun that I've had the last few weeks and that I'll hopefully keep having for the next few months. So up next, I'll walk you through some of my schematics and my thinking. And if you like it, you can always go to GitHub links that are posted down below and download some of the stuff yourself. I haven't exported anything to PDF yet, and I haven't found a way to export it to KiCad or any other software yet, so you'll have to have an Altium license to look at the design files outside of this video. But I'll look into fixing that as soon as possible. So let's go and have a look at the schematics.
First of all, apologies if the sound quality is slightly worse than normal, but the headset that works best with this computer is a bit worse off these days. So the state of the project is basically that all of the schematics on physical paper are completed. I just have to find a few part numbers with the values that I calculated, and then I can copy everything or the last bits into Altium. And the zoom is a bit weird maybe of the program, and that's basically because I had to stretch the screen a little bit so you can't see whose login I'm using for Altium or what kind of other stuff is going on my computer in the lower bar. And I don't have a lot of time anymore to figure out a better way of doing that. So we start with the project, which is shown over here. There's one top level sheet. I can show you by folding it in. Now the board is still empty, so I won't open that. That'll take a little bit of time. And that top level contains a lot of other subsheets. You can see that they're subsheets by the fact that they are of a specific look. They're green with yellow arrows around them. If I zoom in on this, you can see that there is arrows going in, which means the signal goes into the schematic, and arrows going out, which means that the signal comes out of the schematic. And there's also weird arrows that point both ways, and that means that they are bidirectional, which means that they can go in but also come out. This is especially useful for things like the I2C bus that's shown here, because both of these lines could be operated from both ends. So the main controller is the master, which basically determines the clock, this line, and the data is already used by both the master and the slave. But the slave could pull the clock low for a small period of time to indicate that it can't receive any new data yet. In a sense, it's still processing or whatever. As you can see, there's a few signals going into the power block from the main controller, as I discussed in one of my first blog posts. And then there's a few measurements coming out. quite a few of the connections on these schematics have changed since my blog post, and a few new posts will be made about what I changed, why I changed them. For example, a few of the controls have changed, I think, or they might still be the same. I have to look it up. But most certainly the measurements have changed, because I only have 6 channels available on the main controller, or at least still available on the main controller. And a few of the things that I'm measuring now make much more sense than the things I wanted to measure initially. And you can also see that there's a V-charge USB in. That's also something new. I decided to add full USB support for a USB-C connector, which means there's a significant amount of power available to the board when you use a proper USB-C charger. And that goes into the charging system inside the power block by a special pathway that I'll highlight in a bit. And we can enter this sheet either through the sidebar here, or we can right click and then go to sheet symbol actions and then open subsheet. Now you can see that this is another sheet with only subsheets in it. I like to work in a clear hierarchical structure in my designs, so that there's no confusion about which parts do what function. So the power control basically has 5 major functions. One is the charging system, which basically contains the battery connection and oh no, sorry, that's just the charging manager. And then this battery manager over here contains the battery connection and a charging chip. That's one of the blocks I still have to implement in the digital world. And here's motor power and support. And it basically gets the battery voltage and then switches a motor power on and off and a high power on and off. A high power is basically a support rail that things can use that are not motors. For example, DC-DC converters elsewhere in expansion boards, etc., etc. And then there's a high voltage, which is a boosted rail. It takes the battery voltage and then adds a few volts on top of that. That's also something I haven't copied in yet, but that has been designed, because that's needed for the motor drive. And I'll show that in a bit. And then there's the board logic power, not completely unimportant. And you can see that the battery voltage goes in and to enable signals. And then the 3V 3 comes out, a 3V backup, which basically allows the main controller to keep running when the 3V 3 is turned off. A sort of power saving system. And then the main 5V, which allows the coprocessor and all of the connected systems to that run. And then there's the analog references, which get the main voltages from the logic and turn that into analog reference voltages. The reason I chose to get the logic voltages instead of the battery voltage is that if I use the battery voltage there, because the references are accurate but can only take a limited input voltage, I'd need to build in another DC-DC converter in that block. Since I already have 2 here, that didn't make a lot of sense. And then the main analog voltage is only really interesting when the main voltage is turned on, because else what are you doing with your reference, right? And the same for the 5V. If that's turned off, what does the coprocessor need an analog voltage for? So the input power is nearly completed. It needs a few tiny tweaks. For example, all of the resistor values in all of the schematics are set to 0, because it's easier to just quickly make one resistor symbol and then just put it everywhere, because I know which size the resistors will be. I have a very large stock of standard 0603 sized resistors, and I can draw a board with 0 ohm resistors, and then once the board is in production I can change all of these values to the correct ones, and then way before the boards come back all of the schematics will be right, and I can easily populate all of the parts that I want to be populated. So for a while these will still be 0 ohm resistors, while of course not all of them will be 0 ohm. And something else that needs to be done is a protection device here, which is called a Zener diode, which limits the voltage that can fall here, because this is a p-channel MOSFET, and when this USB charge in, for example, is 20 volts from the USB-C connector, and this n-channel MOSFET turns on, then there might be a 20 volt difference between these pins, and many of these types of MOSFETs don't really like more than 10 or 12 volts across there. So by putting an element here that always limits the voltage to 9 or 8 volts, I can protect this device, but I haven't drawn the footprint for that yet. I need to draw footprints and symbols in libraries, which I can also quickly show. For example, in the off the clock library. It takes a little while to open because there's 3D models in there as well. This is one of the components that you can just download from the Würth website for your design. Würth has a very, very large collection of libraries on their website for all of the parts that they sell. And most of the parts get a library at least for both Eagle and Altium, so you don't have to draw anything. And now if I press the 3 key, you can even see that they took the effort of... Oh, you cannot see it. I guess it's not recording the 3D model for some reason, or the recording is blocking the 3D model. I don't know what's going on, but yesterday this worked fine. But Würth actually includes a very accurate representation of the part in 3D. As you can see from the red outline, it has approximately the right height. This is a, I think, female header. If I look at the outline of the 3D body, that's one of the headers that I used to build a charging footprint. And we can quickly see if it does want to open its own 3D models. This is one of the footprints I included for the Atmel microcontroller, and yeah, you can see that that does get the very simple 3D model that the system generates itself for a chip. And for more complicated parts you could rotate it. And the fun thing is, in the PCB later you will also be able to see that. And for every part that I use, I need to create a footprint like this and a schematic symbol like that. And those are in libraries, and then you can place them wherever you want. And then if something changes in that part, for example, you have a 10K resistor and you want to change suppliers, or maybe even the brand of the 10K resistor without changing any of its properties really, you can go into the library editor and then open the properties. And then you can right click and say update all of my schematics with this component, and all of your components will be updated to the new type. You don't have to go through all of them. And that's the beauty of libraries. Almost any computer-aided design package has them. It's not unique to Altium or Eagle or anything else. Libraries are basically the base of electronic design in these kinds of programs, and a program that doesn't support any type of library is basically something you should never touch for designing schematics or boards, because that's pointless. So we were stuck with the power. Unfortunately, I opened all of the schematics to make it load quickly, so it's a bit harder to remember where I was when I drift off in these tangents. But I believe we were in the input power. Ah, yes. Now, this thing here is a bit of a tricky thing to easily explain. This basically amplifies, let's put it like that. That's pretty much what it does anyway. It measures the voltage here, and then the voltage difference here is amplified by 200 on the output. If this pin is higher than this pin, the voltage here will be positive compared to this reference pin, and if this one is higher than this one, this pin will be negative compared to this reference. And of course this is its supply pin and the ground pin, and this capacitor is just there for decoupling, so that it can operate quickly without needing the power to come from all the way wherever the USB ends up being. This capacitor will be very close to that chip to supply all of the fast changing currents to that chip. More on decoupling at a later date, probably. So the reference is created here with a diode. Basically this means I get 3 voltage sources and they combine to create, let's say, 0.7 volts. And then if the voltage here is higher than the charge output, so if the USB is the highest voltage basically, or the winning voltage, this pin will be higher than that pin. Sorry, this pin will be higher than that pin. And then the output will become positive, and a positive voltage on this gate of the N transistor turns it on, and that pulls this pin down compared to that pin. Then the P channel turns on and they start equalizing. And with the 200 multiplication, that should balance out at about 18 millivolts across these pins. And the moment this voltage starts becoming higher than that voltage, because current might want to flow back once the USB charge disappears, or once it becomes lower than the collected output, because this is the output of the block, which you can see here. And that's connected to all 3 of those diodes, because this is basically an improvised ideal diode. I've never tried this trick before with a current measurement amplifier, but these tiny chips support quite a high input voltage, and they're cheaper than op amps that are good enough to do the same trick. So I decided to just use those chips and see what happens. If it goes wrong, I can always take out the MOSFET and put a diode there, and I'll have some losses, but at least the system will work, and this way I can try this this little trick on a fun project and see what happens. This might be a perfect way to create a cheap ideal diode. Instead of using a €3 chip, I used a 60-cent chip to basically do the same thing. And of course 1 5-cent transistor extra, or probably less than 5 cents. So there's another one, and this is actually the footprint I created for the wireless energy receiver, because that's of course the main interface that this whole project started about. So there's 2 pins, the V out and the V rect, and I still have to look up if I need to connect the 0 volt DC somewhere, maybe to the ground, or I haven't figured that out yet. But here's two 0 ohm resistors that allow me to select which one I want to route into the ideal diode. And especially because these voltages are quite low and USB can be a quite low voltage. That's why I decided to use ideal diodes, or nearly ideal diodes. Because a normal diode loses you anywhere between, usually for power signals, say 0.4 volts to 0.8 volts, or even up to 2 volts if you use a traditional diode at a high current. And that's always lost. So if this is 5 volts and you have a diode that loses you a volt, you only have 4 volts, you've lost 20% of your power. Whereas these ideal diodes, if you manage to control them well and the MOSFET that you're using can support the current that's flowing through, you might be able to limit that loss to 0.1 volt or much less. In my case, I'm hoping for 20 millivolts, which is 0.02 volts. And that's a negligible loss even on 5 volts. So that would be great. And I added an option for external power. I still have to add in the connector for that, but it will be a simple standard barrel jack. Because basically, say you have one of these boards made at whatever surface you want. I don't know how many people will, because some of the chips on it are not very cheap. But someone might. I don't want everyone to have to find a specific power source to be able to start playing with it. So I decided to give a few options. Of course, the wireless energy is what it's all about, and that's what it's made for, and it'll include quite a few tactics in its firmware when it's nearly done or completed that aim at charging at a wireless base station. So it will try to find it, and it will determine how much it needs to charge still, etc., etc. So this will still be the, but I felt it would be unfair to not also use USB or external power on people who might not readily have the option to use wireless power. But it will definitely make the robot a lot more fun. Now, going back to the power, we have the battery manager. That's one of the things that's not finished yet, but I'm going to show you everything, else you'll feel I intentionally skip stuff. So there will be an LTC 4020 4020 in here, which is a clever little chip, and that's one of the most expensive ones, if not the most expensive, which takes a voltage between, say, 5 volts and 30 volts and charges any battery that you correctly configure using resistors. So you could say, I have a 2-cell lithium battery, or I have a 5-cell lithium battery. It'll happily charge them all from whatever voltage you give it. Of course, the efficiency will differ a bit, and the maximum charge current will differ a bit, depending on what power supply you have and what battery you have. But basically, it can nearly work with any scenario. Actually, the chip itself works up to, I think, a 60 volt input, at least 55 volt input. The 60 volt might have been its absolute maximum rating, which you usually don't want to touch. So you could even charge it from a 48 volt rail. Unfortunately, some of the other parts that I chose that are also connected to charge voltage and battery voltage are limited to, say, 28 or 26 volts. So I've chosen to assume a limit of 24 volts on either side. For example, I'm currently assuming that the 20 volt USB-C power will be the highest one on the board on the input side, and that a battery might go up to 24 volts on a lithium iron phosphate battery. But that is basically the limit, because at much higher voltage all of your motors will draw such extreme currents or have to have such high inductance that it's already unlikely that you'll go above 15 volts, but I'll talk about that more at a later date. And then we have the motor power, which basically is again a simple MOSFET, a much more powerful one though, that you can turn on and off with the main controller by toggling this pin. This goes up to 2.5 volts or more. This MOSFET starts to turn on completely, pulls down the gate of this MOSFET, and then this MOSFET turns on. That goes into the motor power switch signal. And if you want to know where that ends up, there's a trick in Altium that you can highlight a specific net and sure. And now you can see some error messages as well, because of course I haven't fixed all of the problems in my design yet, so it complains at me. But now you can see that every wire connected there is turned pink, but also there's a pink one down here. So this is a pretty cool feature in Altium, and again many others have it, but it's very good to be aware of such things existing, is that you can highlight this in any color you want. I usually choose fuchsia because you can still see it when you're zoomed out quite far. And that's convenient when people make very big schematics. I think mine isn't that big yet. Nah, this is still doable. You can probably use all of the colors here. Because the fun thing is, it also works through all of the schematics. So if something is connected, I'll have to zoom in a tiny bit, through the barrier of certain schematics. Well, you know what? We'll just take the motor power. And there you can see. It took a little while, but this one turned green because I turned this green on the top schematic. So you can very easily trace all of your signals that way. Unfortunately, they only have a few colors. Oh, actually, you can do custom now. As you can see, I got used to some features quite long ago and stopped looking at new options. Anyway, that switched motor power then goes into another one of those amplifiers. It's exactly the same chip, just a different edition that has a built-in 50 times amplification. So current that flows here goes through these resistors. I did, of course, change these to the... Tiny mistake there. I did change these into their right value because these are very specific resistors that I don't have on a reel, and I just ordered specifically yesterday, which will be delivered tomorrow or the day after. So I did add those footprints and those schematic symbols so that I don't accidentally update them with a standard small resistor that will basically go up in flames once a peak current of 40 amps tries to go through it. Because I've designed all of the powertrain to support peak currents up to 40 amps to allow heavier motors to power up without any problems. Now then you can imagine that if a current goes through this resistor, through Ohm's law, there will be a tiny voltage difference because this is only 5 milliohms. So 1 amp through these two in parallel will only create 2.5 millivolts. And amplified by 50, that becomes, as this signal says, 125 millivolts per amp. And these are two equal value resistors. They are now as well, but they are intended to be 10k each, which means that this signal is divided exactly by 2. And that's because this chip doesn't exist in a 25 times version, and I didn't want to specify another supplier because basically this is easy. If all of your footprints are the same, you can quickly swap out different types, the 50 for the 100, for the 200, etc. So to get it to a amplification of 25, I divide it by 2, and then you get 62.5 millivolts per amp, which allows the main controller to measure to quite a high current, but still with a very good deal of accuracy. So that way the main controller can keep an eye on that motor current, and if it gets out of hand, it can just turn all of the motors off without disabling anything else. Then there's the high power voltage, or the support voltage. Some of the names are a bit confusing across the sheets. I still have to fix that because I've had a lot of things on my mind recently, and when I get home at 10 or 11 o'clock, I don't always remember exactly which names I was using. But that's easy to fix later once all of the details are in. So again, this has a pass transistor that I can turn on and off. I'm not entirely sure why it doesn't show its name anymore, but it's basically a lower current version than this one, because this needs to be able to cope with 40 amps, and this is only designed for a couple of amps. As you can see here, because this is a resettable fuse, which is of value 2 amps, so this high power will turn off, or will fuse itself above 2 amps, about 3.5 amps probably, because these things always trigger a bit later than their normal usage voltage, current, excuse me. So this is inherently protected and doesn't need the main controller to perform any intervention, because this is basically assumed to be a small support supply that allows plug-in boards to create their own different voltages than the ones that are already created on the board. So it's also not accounted for in power consumption in the robot, because the assumption is that it's never going to create an error of more than 10%. Probably not even that. Now here, this is the boosting circuit, which is also not drawn yet. There we go. As you can see, nothing in it. And then for the analog references, there's some trickery there, because I wanted the coprocessor to be able to work off 2 references. So there's the 4096 millivolts, which is 4.096 volts, because that processor runs off 5 volts, so it can handle an analog reference of this number, and this is an exact implementation of a 12-bit number, or this is a 12-bit number basically. So that means that if you measure a 12-bit, 1 bit is exactly 1 millivolt, which is pretty cool. But then it can also run off a 2.5 volt reference. So there's an enable analog signal, which basically turns off these 2 MOSFETs, and so when you disable it by pulling this low, these nodes will go high, and this MOSFET will pull down this pin, and the thing will go in shutdown. These chips have a shutdown where the output becomes very high impedance, so they won't pull any current from the other one. But of course this one turns on as well, and that means that this shutdown goes low, and that turns off as well. Of course, when it's enabled, this one's high, these 2 MOSFETs turn off, and then this pin is allowed to go to the value that ref select is, so either high or low, which gets inverted again by a standard MOSFET, which means that by toggling the ref select over here, you toggle which one of these chips is turned on and goes to the coprocessor. You can also see a special indicator here, because I'm on the European continent. I feel I'm allowed to use UK English, but that's a net directive which you can place in your schematic, and it has a name, and this is not to be confused because a lot of beginners are confused. The name is not something you see in the board later, but you can set variables. For example, the class name, which is the default variable, you can set that to Analogue, and once you've set that, if you export that to the board later, you can use that class name Analogue as a net class to give them special rules. So you could say, I want this to always be close to ground, or I want this to be far away from things that are noisy, so that the feedback path is nice and noise-free. There's a tiny purple thing in here, and that's a net tie, which is basically went off screen. Basically a small net tie, 6 mil. That's a size. That's 1 mil is 1/1000th of an inch. So this is a 6 mil with tiny bit of trace that allows me to have two different net names without getting conflicts later. And then I can, by putting this net tie somewhere specifically on the board, I can decide where that feedback is measured, which allows me to play around. And then the main reference is quite simple. Just supply in, go through a filter bead to take out any noise that might be present, and then two capacitors to take out some more noise and supply a fast current loop into this chip. And that goes to the main controller's analog, again with these net directives. One for analog and one for analog power, because I might want to treat them differently later. And I can do that now. That's all of the analog stuff. So we go into the subsheet for the board power, board logic power. You can see that they contain a subsheet which will be a buck or reducing DC-DC regulator, which gets the battery voltage and can be enabled or disabled. Can be trimmed to a specific voltage by a pull-down resistor, and has an output voltage which then goes into either of the systems. And again, the current is measured across a resistor. In this case, a standard 0603 50 milliohm resistor, because there won't be a lot of current and can easily handle it, or it might actually be an 0805. Oh, 1206 even. So I already ordered that because a 1206 is a standard package. Again, I used the 0 ohm trick, but I already placed an indicator for myself for later that I want to put the 50 milliohm there, so that I get these numbers, the 2.5 millivolt per milliamp. So that again the main controller can keep an eye on what happens there and maybe decide to turn off some things if things turn out to be going wrong. And then there's the backup voltage, which will be either a onboard lithium battery, a small one of those coin cells that you can't recharge, or chosen through a jumper, a regulator that has a very low current drain when it's not being used, so that you don't lose a lot of power that comes directly from the main battery. So you can choose which one you want to use for the backup voltage. Then of course that backup voltage needs to be monitored in case it is a second battery. You want to alert the person that's using the robot when the battery is nearing empty. So the main controller needs to measure that. And of course, the problem there is if you put a resistor divider directly on that backup voltage, you'll use some extra current there. So I added an op-amp that's powered by the main voltage, and we'll get an input resistor of probably 1 megohm. That's one of the very few things I haven't calculated yet. But 1 megohm here, and a compensation resistor here. But basically this op-amp mimics the voltage that it sees here on its output. There's a lot of explanation about voltage follower op-amps on the internet, and you can look that up. This resistor is not necessary in theory, but because there's a very big resistor here, there needs to be a sort of compensation resistor here to compensate some tiny little offsets and errors. And I might actually put an extra resistor here just in case I need some tweaking there as well, but I don't expect to. This number for the op-amp isn't necessarily correct. This is just the one footprint I had laying around somewhere in another library that fits several other op-amps that I have in stock. So I just placed this one, and I'll figure out which one is the best for the situation later. Now that becomes a buffered voltage, which is a lot stronger and powered by the 3V3 main, which is the key. So I can then divide that by half with two 10K resistors and put that in the ADC of the main controller. Because had I used 1 megohm or 10 megohm resistors to divide this backup voltage and put it in the ADC would have had so much leakage and needed so much current to do the conversion. There's a lot of explanation about how that works as well on the internet. Then that voltage would have always been measured incorrectly. So that's why I use this trick. And then of course we have the little buck converter, which for some reason it doesn't always open the right sheet. Nothing connected yet, but the parts are there. Or at least I'm missing a few small parts, but not many. And this is basically a chip that drives a P-MOSFET to reduce a voltage. A high voltage comes in from the V-in into that MOSFET and a few pins on this side. And then it measures what happens on this side. And keep moving stuff around while pointing. And it measures some voltage on this side. And then depending on whether this voltage is right or not, as set by external resistors here, of which one will be connected to the trim port, it will either turn this MOSFET on or off, and that makes it so that you can set a specific voltage here, because if it's on a tiny bit of time and then off for a very long time, because there's an inductor and a capacitor, bank of capacitors here and an inductor here, that smooths out that peak and that long period of nothing, and then the voltage over here would be lower. Unfortunately, had I had all the wires here, I could have shown you, but it's already getting very late and I didn't want to wait too long to do this, so they're not there yet, unfortunately. So that's the logic power, and we've had all of the other sheets on this sheet, so we can go back to the top level. And now most of it will start going quite quickly, because that's quite a big portion of the clever stuff in this sheet that isn't mainly firmware. Because this is the main controller, which is really very standard, just the signals are connected to ports. I'll just quickly disable all of the net colors that I just turned on, and then you get the errors again. And there's a bit of trickery here to get the 3V3 main power and the backup power into the microprocessor. So there's a main voltage coming in, which gets filtered and put through a diode onto the I/O pins. That's okay, because this diode only loses about 0.3 volts, so this will be 3 volts at worst. And at 3 volts, this processor still works at its perfectly maximum speed, no worries. So then there's a transistor here, a small MOSFET, so that if there's a backup voltage present, there's a small diode inside this MOSFET, which has a forward voltage of, from memory, about 0.8 volts. So that backup will then charge up this point, and again this point compared to that point determines whether this P MOSFET turns on. And then if the main voltage disappears, this node will very shortly drop to backup minus 0.8 volts. But before it really gets a chance to drop significantly, this voltage will be gone, because this diode blocks any energy going that way. And then this voltage will become about 3 volts or 2.5 volts, and this MOSFET will start to turn on and actually conduct better. So the backup will start supplying the main controller without any losses anymore, because this processor doesn't have a backup power pin. And then there's also the USB power, which gets powered by the USB connector, as well as the 3V3 main. And as you can see by this node, there's still a power loop there that I discovered when I was entering the schematic from my node. Of course, it's easier to make mistakes on paper, because nothing verifies what you're doing. On paper, you're allowed anything. And the rest is just input and output signals. And then there's the USB schematic. Again, it doesn't open it. So there's the USB-C connector, provided by Würth, or hopefully provided by, or at least made by, if I have to still pay for it. Because at the moment I'm not entirely sure how this whole pair 1 and pair 2 thing works on the USB-C connector, because it has a USB 2.0 data pair on the top and the bottom, because you can reverse the plug and then it should still work. So I think on my board I should be connecting them both together into my controller, and find a way to do that so that it doesn't create any errors. And for that I created a new net directive, which is maximum length 20 millimeters, which means that these traces aren't allowed to be too long. There's a bit of filtering here, which is designed for USB 2.0. It's a nice small coupled inductance that Würth also makes, and of course this is also a weird part that clamps that voltage on that line to 5 volts compared to ground, so that spikes don't hurt anything. But if this length is about 20 millimeters, the USB signal should still be performing quite well. Because normally if you have a say that port number 1 is connected, if that's a high speed signal, you basically want it to go this way, and anything that's connected here will act as a sort of an antenna. And the longer that antenna is, the bigger your problems will become. So realistically, from this node here, on this P line, you would really want it to not go there at all. But if it has to go there, you can make a directive that at least tells you when you're layouting, keep this trace as short as you can. And then there's a special directive that indicates that these signals form a differential pair. A differential pair is basically two wires that operate together but inverted. So when the P is high, the N is low, and when the N is high, the P is low. And those signals usually have a very specific impedance, and you can get that done by coupling them together all across your PCB. And you can use that directive for that, and then you get support when you're layouting it recognizes that it's a differential pair and then allows you to set some rules so that you get the right impedance. And then here's a little bit of trickery to get the USB voltage to go both ways, because I also want it to be able to be a host to whatever you want to plug in. And whether or not the firmware supports that, that's a second question, of course. To be able to support USB-C chargers and devices and whatnot, I need to do some trickery with detecting and driving signals on this USB-C connector. I have found a $1 chip to do that for me, initially made by Fairchild, now part of On Semiconductor. And that basically configures all of the signals going into the connector and allows me to send some signals in and out of the extra support channels by communicating with it through the standard I2C port that's connected to my microcontroller. That means that I can tell a charger, hey, I want 20 volts and 2 amps, if you can supply that. And then my USB-C connector can actually charge the robot with a level of 40 watts, which is quite nice. So there's a, this chip, by the way, doesn't do any of the data packaging. I specifically have to tell it to send this bit of data now and do this and do that. So it needs to be developed entirely in firmware, because a chip that would do that would also have been $9 or $10, and I mean, that makes a board more expensive where it doesn't have to be. Especially if other people want to start building them. You have no costs of downloading the firmware once I've implemented that functionality, whereas that $9 for a chip you still always have to pay. So this is the incoming USB voltage. It goes through a tiny bit of filtering, and that then again has a switch that allows me to turn on that voltage from the microcontroller. By default it's turned off, so that I don't power anything that I don't want to power before I want to power it. If that sentence makes any sense to anyone. And then there's the 5 volts on the main board coming in here, again being filtered, because I don't want any noise coming from here into my system. And then there's 2 P MOSFETs, that, because again there's a small diode in there, that little arrow here indicates that there's a diode connection here, which is inherent in the structure of standard MOSFETs. There's MOSFETs with these 2 pins routed out of the package separately for very special purposes, and then you can connect this diode elsewhere and not have it bother you. But those are expensive and or hard to find, so you use normal MOSFETs because they're several orders of magnitude cheaper and easier to find. But then you have this diode, which would have meant, if I only put this one, that this voltage can always flow right into my 5 volt main, which is quite painful if this happens to be 20 volts. Had I only had this one, my 5 volts would always be powering through this diode, would also be powering the V-bus, which is also not good. So you put 2, because this diode blocks that one and the other way around. And once this voltage goes up, it charges up this point, and this resistor then pinches off both the channels in the MOSFET. And then by turning on this signal, this MOSFET opens both of those MOSFETs up, and then it can power the V-bus with a protection fuse of 350 milliamps, because I don't want any badly designed hardware to break my robot. And of course over here there's a protection diode for the V-bus, so that if there's high spikes there, it clamps them. And that's all that's to the USB. And I can go back to the main controller, and we can see that there's nothing special there. This will be the JTAG connector. I have to route that out to the right signals. because Atmel makes a nice 1.27 millimeter 10-pin connector, or uses that for their JTAG signals on the latest programmer, which I hope Microchip is also selling, so that other people can also still buy it. I have one for myself. I bought a year ago. So going back to the top level, there's also a coprocessor, which is also not hugely complicated. As a schematic, again, there's the 2 bits of processor with all of the signals. And there's the power supply. On this one it's all neatly routed out because there's no weird switching. Well, neatly, relatively neatly. Again, the JTAG connectors still have to figure out what goes where. And then there's level conversion, because the internal bus, as we remember from some of my blogs, is 3V 3, and this processor works at 5V. So these are level translators that work with bidirectional signals, and anything that comes in at 3V 3 here becomes 5V there, and the other way around. So all of these signals get echoed, and the main processor distributes a very accurate clock that it creates with its crystal. That gets used by the coprocessor to also run quite accurately, but this sheet also outputs that so that external devices can choose whether they want a 3V or a 5V reference clock, or just not use it at all, because that's also perfectly fine. All of these processors have a internal oscillator that you can also use, but they are not very accurate, whereas a crystal oscillator is usually quite a lot more accurate. So I decided to route that out over the board into all of the external connectors. As you can see here, the clock 3V 3 and clock 5V, so that every thing that you plug into the robot will have access to an accurate clock, or at least a clock that everything agrees on. And that's a nice thing to have, I think. Then there's the position sensors and a set of spare signals that I called XCon, and there needs to be a connector there. It will be a pluggable SFP connector, which allows you to just push in a 20-pin circuit board. So anyone who wants to make a board for that doesn't have to buy any special connectors, just have the right footprint, which at some point I'll start providing for as many packages as I can get a hang of and my hands on. And then there's the back bay and the front bay. Again, nothing there yet. These will be M2 or M.2, I'm not entirely sure how you pronounce that, connectors, the ones that are in laptops to allow you to put in small SSD drives, etc. Because they are also quite affordable, 60 or 70 cents, and have 60 pins. So I can route out quite a lot of signals. And that's convenient because these boards will have motor power routed to them with quite a lot of current, and that requires many pins. So again, that's a connector for which you can just design a board with the right pin out, and you can shove it in, and nothing required from the user. I really wish I could say I bought it from Würth, but Würth only makes connectors that have a mate, unfortunately. In this video, my suggestion, Würth people who should be watching this at least once, make some connectors that you can shove a PCB in, because they're super convenient. Anyway, until they do, that's supplied by AMP and Molex, those two connectors. And I would have genuinely preferred to have it from Würth, because my Würth supply line is much easier than the ones for any other connector. And undoubtedly I could have convinced one of my local reps to supply it at a cost close to what the cheapest Molex cost. So why not, right? Now the coprocessor routes out to motor control as well. I've moved all of the motor control into the coprocessor because the main controller just didn't have enough signals in the analog domain to really allow me to properly control motors in the way that I wanted. And I've limited the number of motors because I went a bit mad with my initial plan, because I only really need one motor for the left side and one motor for the right side. And then I had sufficient signals left to have one 3-phase motor or two 3-phase motors that allow me to just run a few propellers. And that way, with just the two of them, I should be able to put it in a sort of Chinook mode, where one of the propellers rotates left and the other rotates right. And by angling them slightly against each other, I should be able to get it balanced. But the lucky thing is, the coprocessor has one analog output, which I can put into this, which is an amplifier basically, which turns a very small signal into a very strong signal. And that can then drive a sort of a tail rotor, so I can also still just use one of these motor controls with a bigger propeller, and then connect a tail motor that puts extra sideways pressure to keep the robot facing in the right direction, like normal helicopters do. Unfortunately, I haven't figured out in that case how I would move forwards and backwards, but I might just do that with inertia, because it's a function to hop over objects and not to navigate through air. So I might just use its existing forward momentum to just jump over things without really aiming the robot anywhere on its propellers. But there's enough control here that I can play around with, and we'll see. And if it needs to be more complicated, I can always make a plug-in board that has another 2 motor drivers, and then it'll all be fine. And these motor drives aren't fully implemented yet either. They have phase drives and, again, current measurement with the same types of chips. And you can see in gray here that it has an extra name for these things. That it does that automatically because there's multiple of this block. So there's multiple of this resistor as well, so it shows me that they have special names until I tell it to create other names. More about that at some later date. But these phase drives have not been implemented yet, unfortunately, or not fully. There's a chip there, hooray. And the same goes for this. This is in the same state of completion. There we go. This level is done. Again, 3 phases, each phase with a current measurement. In the 2-phase system, there's only one current measurement per phase. And I do a little trick there, because I want to divide by 2 again. But this time I give it the full analog reference. So let's say that the analog reference is 2 volts. Then if it measures such that this output would become 4 volts, this divides to 2 volts. But if the current goes in the other direction, in the same magnitude, it will subtract that 2 volts from that analog reference, and this becomes 0. So you get a 0 to 2 volts output for negative to positive current of the same magnitude, which I could have also achieved by taking this output directly and put half the analog reference voltage here, because then it amplifies positive, negative, up and down, compared to that half reference. But then I would have had to put a smaller resistor here, and all of the errors become larger, whereas this way I can just use the times 50 and then divide by 2 again, and everything's fine. So this can actually measure current going that way or current going that way. So I only need one measurement for one loop, because a loop of a motor will be put here and one here. So current either goes that way or that way. So with only 2 measurement circuits I can measure everything I want. And for the 3-phase it's just easier to, at least in the first version, to have all 3 of the phases, even though current will always go out of one into another or into 2 others. depending on the control scheme that you do, it's easier to be able to measure them all, at least in the first board, and we can always optimize them out when I go into a sort of production mode. And this note here is basically, you saw it on another sheet as well, tells other people that I intentionally did not repeat this block, because you can tell Altium to repeat this block 3 times, then it becomes a stacked thingy, and then you can have the signals and separate them, and there's all kinds of fun things you can do there. But I have learned over time that more junior designers get completely confused by that, so I decided not to do that, and add this note here in case a more senior designer looks at this to decide whether he wants to outsource something to me and thinks, he doesn't even know about repeated blocks. Unfortunately, of course, this note might then again confuse junior designers, so I might have just defeated the point there. And then the back bay is again not implemented, just like the front bay. And let's see, the battery manager we've looked at, so the only thing left is the voltage drive. As you can see, it's not fully done either. This is basically an H-bridge driver, or a half H-bridge driver, which I'll also use in the motor control for each single phase. So I decided to reuse that here rather than get one chip that does all 4 of these transistors. And I'll explain that further at a later date. But basically this is a DC-DC converter, just like the other ones. It's the same schematic as well, but with a different trim setting. And that trim setting has a side branch from the V control. The voltage output of the coprocessor goes in here and basically messes with the trim setting of this DC-DC converter, which makes it go up and down on its output. And that way I have a 1 amp DC-DC converter that I can force to do whatever I want with this control voltage. And it's powered by both the high power and the motor current, or motor voltage, because I want to be able to use this for whatever purpose I want when either of those signals are turned on. I used 2 simple diodes there because I assumed that these would be at least 12 volts in most cases. And then at 5 volts 1 amp the losses here are limited, and I didn't want to pepper the board with pointless ideal diodes everywhere. And that's basically how far I got to date.